Howdy. So, Chapter 4, Fun Chem 1. Here we go. We're going to revisit some of these ideas of chemical equations, chemical reactions. Get ready for next week's lab. This week's lab, remembers online, a lot of calculations, a lot of practice on what we talked about with doing, fancy word for it is stoichiometry, but those conversions from grams to moles. So you want to make sure you practice those. And now we're in the concept section. We talked about chemical reactions last time. Let's kind of review a little bit. I'm going to start with our idea of diatomic elements, because we're at the point we're getting ready to put a bunch of concepts together. So diatomic elements, I'm going to look at real briefly on these. What we're looking at is hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Remember, there's 7 of them. Hydrogen, then you come over here and you make a number 7. Alright, so anytime you see those diatomic, orange, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, I'll always refer to those, for instance, as hydrogen gas. And what's nice about those is if they're a free element, if they're found by themselves anywhere in a chemical reaction, hydrogen will always be H2. Keep in mind, H2O, this is not a free element. This is part of a compound, and so it just happens to be a 2 here. So when we have C5H12, when I refer to this, I'll just call it hydrogen. But if I say hydrogen gas, I'm talking specifically about the diatomic free element hydrogen, H2. Alright? All of these are gases except iodine. It's actually a solid at room temperature. Hold it in your hand and it skips the liquid phase and sublimes to the gas. So it's actually quite interesting. It's pretty cool. So the reactions we're going to be looking at today, so we had our reaction types. So if I go back and review these, oops, too far. We had our reaction types. Let's just click here. There we go. There they are. General types of reactions. Alright, so the reaction types, we want to memorize the archetypes for it. So we've got them broken down in the lab, we've got them broken down in the PowerPoints, in the book, all kinds of them, but you really just kind of need to memorize these. So in this chapter, very helpful to have an idea of what you would want to write down on a piece of paper. If I gave you a test, what would you immediately want to dump out in terms of a data dump? Alright, and so things, these reaction types, then we had a combination or a synthesis, and we said that was A plus B goes to AB. Alright, so an example of this might be hydrogen gas plus oxygen gas goes to H2O. Not balanced. Let me go ahead and balance it real quick for you. There we go. So just making water. Easy enough. Can't do that one in school anymore. So hydrogen gas burns, but when you mix it with oxygen, do this reaction, it's explosive. And we always have trouble with the cinder blocks, causing a lot of echo. So they don't let us do that inside. Can't do it outside anymore. Please come running as soon as you make any kind of loud bang. So times we live in. Next thing we have is an analysis or a decomposition reaction. And it's just the opposite. We're going to break something apart into its pieces. Those two, you'll never have to predict the products. Just balance and recognize it. Then we had a single displacement. single displacement. AA plus BC goes to AC plus B for, we'll do that in 2 weeks. In lab, we may even have to speed that. I may have to speed that up just so that we can try and get some practice on the pre-lab for it. But this is one of the tougher ones to predict. A is going to be 0. B has some kind of positive charge. Sorry about that. My lab partner decided to tell the garbage man he needed to recycle. So please recycle. So single displacement's toughest to predict, mostly because we have this change in A going from no charge to having a plus charge. C is just along for the ride. And so we have a transfer of electrons. And we'll talk about this again in chapter 8. It's an oxidation and reduction. So a transfer of electrons will come back and hit this. But for us, it can be a little bit troublesome just because trying to get the charges predicted makes it a little tougher. All right. Double displacement's actually easier because whatever the charge is on the left hand side, it'll be that same charge on the right hand side. Got a big old whiteboard and I still managed to go downhill. Oh well. So double displacement AB plus CD goes to AD plus CB. A and C have positive charges, B and D have negative charges. They'll have the same charges on the other side, we're just swapping partners. And this idea about swapping partners is going to be very crucial to us because when they got new partners, they're going to get new subscripts. My advice on this has always been to tell you that I wish I had known way in the past this advice, but you never do anything with your new partner that you did with your old partner. It's especially true with girlfriends, because they really get mad when you forget and call somebody by the wrong name or say, hey, remember when we did? Oh well. So they'll have new partners, they'll need new subscripts. So don't bring over the subscripts. The only exception to that is when we have polyatomic ions. If the subscript is part of the piece, we bring that over, but we don't bring over to the subscript tell me how many of those pieces I have. So it gets a little confusing. Just pay attention to parentheses. Make sure you've memorized your chapter 3 polyatomic ions. It really helps in this if you think of them as pieces. So writing these out, and if you think of it in terms of A to B instead of, for instance, NH4 to S. Alright, and so this makes life a little bit easier. You can see it's an AB. Okay. So other reaction types then we have to deal with. We said combustion was our most common one to ask about in terms of first word problems. Alright, so combustion, take your fuel plus O2. We love to ask this for balancing reactions, and almost every balancing reaction we do is based off of this. So combustion reactions, we'll give you the fuel and we say something like burn or burns or burning. Combustion, we just have to give you the fuel. Keep in mind this is assuming everything is burning completely, which it doesn't always do. Move my mouse cord out of the way. You'll quit focusing on it. So in real life, not everything combusts completely. It'd be great if it did, but even the CO2 itself can be a problem. So we're learning that just the actual making CO2 can be a problem. All right, so we did those. The new one we're ready then for is a precipitation. And we said all of the precipitation reactions that we see will be double displacement. So let's go ahead and get into our PowerPoint view here. So a precipitation reaction. Whoop, don't want to use that anymore. Okay, so precipitation reaction, it has to form one or more solids. And the way we predict that is by things that are insoluble in water make solids. Nice and easy. So here's an example precipitation reaction. We'll actually be scheduled to do that, this one in this upcoming lab. But potassium iodide says they mixed it with lead 2 nitrate and gave us this nice pretty color. This is actually a pretty cool lab just because this reaction happens instantaneously. As soon as you mix some two clear colorless liquids, you get this beautiful yellow solid. And so it's nice thing to begin with. Now here we can say that no reaction happened. There was a double displacement that could take place between sodium iodide or potassium iodide and sodium chloride, but both of the products are soluble, and so they stay in solution. And what's key about these ionic compounds is if it's ionic and it's soluble in water, it will dissociate. And so the ions that we had in solution when we started the reaction, we have those same ones when we end the reaction, and so nothing really happened. So let's go back to our original idea here of this first reaction. Potassium iodide, as soon as I throw in the potassium and the iodine, they go in, they dissociate. So the potassium's floating around, the iodine's floating around, and when they bang into each other, they can form potassium iodide again. But it's soluble in water, it immediately dissociates back out. Lead 2 nitrate, for each lead we have 2 nitrates. That's just based off of their charges. All right, we can tell that it's going to be soluble in water. It's got this AQ, tell me it's soluble in water. Aqueous, all right. It dissociates, and so when we mix them, they're all floating around, and you'll never have the lead bang into the potassium. They both have positive charges. They repel. They don't want to be close to each other. And you'll never have the iodine and the nitrate bang into each other. So as these float around, there's only a couple of possibilities. The iodine can only react with the potassium and the lead. So if it reacts with the potassium, it forms that potassium iodide. We already saw that's soluble in water, and so it immediately falls back apart. Nothing happens. All right. If it hits the lead, it's going to form a complex. And once we have 2 of those iodines get attracted in, now it's going to form a compound that's not soluble. And so that's really all this is a double displacement. So I've got an A and a B plus a C and a D, and we're just going to swap their partners. All right. Notice this iodine, when we brought it over, it has a new subscript. It has to have a new subscript. It's got a new partner. Lead has a +2. Iodine's got a -1. You need 2 of the iodines to cancel that charge out. Lead is a +2 on the left-hand side. It's still a +2 on the right-hand side. Potassium goes with nitrate, +1 and a -1. It's 1 to 1. And so when we do our crisscross and reduce the ratio, it's still 1 to 1. And so that's why when we brought this over, we brought the 3 because it's part of the piece, but not the 2. New compounds, new partners, you need new subscripts. All right. Now, we have 2 of these that could potentially be what our yellow solid was. And so what we need to do is learn how to predict what that solid is going to be and which one's going to make a solid. And the way that we do that is with solubility rules. Now, on my test, I give you these solubility rules, and the same ones that are here, they've run away. All my tests have run away. That's what I'm looking for. Aha. So what I'm looking for then was on solubility. Here's my periodic table. On the back of it, I give my solubility rules. Two different sets of rules. Alright, so the ones on the top are soluble unless, and the ones on the bottom are insoluble unless. And the key to reading this is the exceptions only apply to the rule on that line. So I'm going to come back over here to a little bit bigger view. Same basic table. So two tables. I've got a table for things that are soluble unless, and a thing for things that are insoluble unless. Alright? And so things that are soluble: lithium, sodium, potassium, rubidium, cesium. I've seen those before. That's group 1. So group 1 except hydrogen, always soluble. No exceptions. Alright? Ammonium. If it's you see ammonium, it's soluble. No exceptions. Love that rule. Alright? If it's got nitrate, HCO3 or ClO3, these things soluble. No exceptions. Fantastic. So here's our iodine, and we can see it's soluble unless it's with silver or mercury 2 or lead 2. Alright, now if it's, notice I've got the charges here. If it's not that charge, it's not, this rule doesn't apply. Alright, so insoluble, we've got these lists. Note alkali metal, keep in mind that's group 1. We can also add ammonium, and down here we can also add ammonium. Let me go ahead and stop us right here. Hey, welcome back again. Sorry about that. Sometimes your boss and your lab partner combine together to make sure that you got to take a little break. So we're looking at our reaction here of we were looking at potassium iodide and lead 2 nitrate, trying to pick out which things are soluble. So as I'm looking at these, I'm going to apply my solubility rules, and want to keep in mind that these are not an extensive list of solubility rules, the actual little booklet of them that you could memorize, but we picked these because they're internally consistent. So if you find one rule saying a compound is soluble, then you're not going to find another rule that says, oh wait, it's not soluble. So all you've got to do is find one rule that applies, and you know that compound. This means there'll be some compounds that these rules don't cover, and we just can't make a prediction on those. You can go to further resources to find those, but I just won't hit you with that on the test. So our first compound then, what I'm looking at here, potassium and nitrate, I need to find a rule that deals with one of those. And so as I go through, here's potassium, and so if I see my potassium, it will be soluble, no exceptions. So I can immediately decide that this is soluble. Alright, and I also could notice that the second rule says nitrates are soluble, no exceptions. Both of those rules tell me it's soluble. And then when I do the lead, I can look through my rules, and I'm looking for, under the rules, nothing that says, I see nothing that says anything about lead. I check my insolubility rules, nothing on there. So I'm going to move on to iodine. And sure enough, on the third rule, it says halides are my halogens with negative charges, that they're soluble unless, and it says unless they're with silver 1, mercury 2, or lead 2. So I need to check the charge on this lead to figure out, hey, is this soluble or insoluble? And so the charge on this lead, 1 times X is 1 came from there. So subscript times charge plus subscript times charge, iodine, group 17, so it would be a -1. And the total charge, remember the total charge has to be given if there is one. There's not one, so this is 0. So some quick algebra. This is in fact lead 2, and so this lead 2 is insoluble. Now I want to indicate these with my states of matter, and this is where a lot of students get confused. States of matter: gas, liquid, solid, aqueous. If it's soluble, it'll be aqueous. Remember, my solubility rules only apply for water. So I can come in and I'll put AQ for my KNO3. It is soluble in water. It's aqueous. The lead 2 iodide, notice I threw that in, had to use the stock system. There is a lead 4 iodide. It's insoluble. So I mix it in, it's going to make the solid. So the S is not for soluble, the S is for solid. Really common mistake. That's the thing a lot of students make the mistake on. So the states of matter, you want S for soluble, AQ for soluble, S for solid, insoluble. All right. So looking at my solubility rules, if it's soluble, this will be AQ, and if it's over on this side, it'll be insoluble, which will be S. On the insoluble rules, so the bottom ones, when I give you this table, these are not soluble unless, remember, IN means not, and so these are going to be solids, and then AQ if they're on the exceptions. Always keep in mind the exceptions only apply to the rule they're on. So the first two rules have no exceptions. Okay. So all right, let's move on to net ionic equations. Whoa, man, this is a big long one. Man, oh my gosh, what is a net ionic equation? Well, when you do your paycheck, you get your gross, which is how much you earned, how much you should have got paid, right? And then you get your net, and that's how much you have left. So either you get the net after they've taken taxes and health insurance and everything else out of it, and oh man, I remember my first paycheck, stop and go, who's this FICA person and why did they take all my money? Or you could look at your net as being after you take out your bills, how much you have left each month. It'd be great if it was just positive 1 month in a row. That'd be great. All right. Well, a net ionic equation is really about getting rid of all the extra stuff. So when we do this reaction, we saw a beautiful. So I'm going to get rid of these rules for a second. Go back up to our beautiful reaction, and we saw this bright yellow. All right. And so the bright yellow is really just about what made that yellow. And so a net ionic equation, we'll start off with our chemical equation. And so, boom, balance is terrible, or focus, there it goes. All right. And so chemical equation that we were doing here, we had PbNO3 2 aqueous. We may have to write it a little smaller. I don't know why that was over in the way again. Plus Ki, that was aqueous, and we said it went to PbI2 solid plus KNO3 AQ. Oh, right off the map. Okay. So let's go ahead and bounce it real quick. So I'm going to use my polyatomic ions. I've got 2 nitrates here, 1 on the other side. I'm going to go ahead, put 2 to get my 2 nitrates. That gives me 2 potassiums. I'll fix that by putting a 2 here. That'll give me 2 iodines. And now I've got 2 potassiums, 2 iodines on both sides. All right. So that's the chemical equation. If you can either balance it at the very end in the steps. I like doing that because sometimes I don't like seeing a lot of my work just get thrown out. On the other hand, if you're the kind of person that has to have everything match up and line up perfectly, you're definitely going to want to balance it at the beginning. So the next thing we do is called the total ionic equation. And a total ionic equation is actually quite simple. We're going to dissociate any ion that is soluble in water. If it's covalent, it stays if it's as it is. If it's anything other than a Q, it'll stay as it is. Side note, we see this all the time. Do not write that. This is water dissolved in water, which is water. Alright, so that one all the time. Okay, here we go. This is just a bookkeeping tool. That's all it is. So I've got my lead nitrate. It's ionic. It's soluble in water. I can tell by the AQ. So that dissociates into the lead plus 2. And if the total thing is soluble, the pieces are soluble. Now notice I'll get 2 nitrates, each one floats around on its own. And we saw this on our slide previously. We saw this in our pretty pictures when we dissociated these. Alright, and then we'll have 2 potassium ions and 2 iodine ions, both of which are aqueous. Okay, keep in mind this 2 applies to both. We had 2 of them together. I've got 2 of each one. Alright, so I'm going to dissociate the other side. Notice the lead 2 iodine will not dissociate, so we just bring it down. Pb I2, exactly as we see it. The potassium nitrate, I'm going to go ahead and write it down here. 2K plus 2 NO3 minus. Both of the pieces will be aqueous since the total piece was aqueous. Alright, so that's our total ionic equation. We will never ever ask for the total ionic equation. What we do ask for is the net ionic equation. Net ionic equation is what was the wow factor, what made the precipitate. So these are for precipitation reactions. We're looking for what went in to form our solid. Alright, now this is actually much easier than you think. This is about getting rid of what we call spectator ions, and these are ions that are on both sides of the reaction exactly the same. Now because I balanced this, we'll actually have the same coefficients in front of them. If I hadn't balanced this previously, then those would be potentially different. So I'm going to look for anything that's the same on both sides. So immediately I see I've got a nitrate here and I've got a nitrate on the other side. Those are spectator ions, and so I'm going to get rid of them. I can do the same for potassium. There's 2 potassiums on both sides. They're both K plus aqueous. I can't do it for the lead. It's aqueous here, and it's part of a compound on the other side. So the net ionic equation is the total ionic equation. You just get rid of any spectator ions. They're there to watch the game. They don't participate. Alright? So Pb plus 2 aqueous plus 2 iodides aqueous goes to Pb I2 solid. This is our net ionic equation. This is what it took to make the solid. Somebody says, how did you make that? It was the lead plus 2 reacting with the iodine. That's our net ionic equation. Welcome back again. Sorry, I had to take a little break there. The joys of working with a teenager. Alright, so we were looking at our net ionic equations, finished those up. We're ready to start putting these things together. And the steps in putting these together, there's 5 steps. And the first things you do when you are exposed to one of these new reactions, the first thing you have to do is figure out the reaction type. And that includes figure out the archetype. So decide, is it single displacement, double displacement, and so once you figure out the reaction type, that'll help you predict the product parts. And so second step then is the product parts. And the key to that is you do not bring over any subscripts. Those will have new partners, new subscripts. So the third step then will be to actually find those new subscripts. Alright, remember that once we start balancing the equations, we cannot change the subscripts. Only on this step. This is the only time. So in step 2, you brought over the pieces. The only subscripts you ever bring are part of polyatomic ions. You're only bringing over the subscripts that are part of that piece. New subscripts, you'll have to look at the charges and balance the charges. Step 4 then will be to go ahead and balance your reaction. And so here you're working on the coefficients, and you're just going to make sure you have the same amount of each element on both sides. Alright, so don't change the subscripts as part of balancing. And then finally you'll look at solubilities, and if they required you to, you could go ahead then and do net ionic equation if they asked for it. So this is putting everything kind of together. That's going to be one of the main skills of getting ready to move forward in this chapter. And so in our lab, we'll see a series of reactions, and we want to go ahead and get a little bit of practice with finishing reactions. And so these show up on the pre-lab, and we want to get a head start on it. So let's start by looking at some of these as examples. Na2SO4 plus BaCl2. Alright, so we're going to do this reaction. We need to go ahead and figure out what reaction type it is. So if I want to go ahead and label this, this is an A piece. It's one piece. Now here I've got a polyatomic ion. A dead giveaway is there's 3 capital letters. So I had to recognize this is a B piece. Alright, that it's one piece together. Orange a little tough to see. We can get it. So AB plus CD. This is a double displacement. Alright, so double displacements. I'm going to go ahead and finish out my archetype. AD plus CB. And that's why memorizing those was so important. Alright, now I can take these pieces. Do not bring the subscript unless it's part of the piece. So my A piece is actually sodium. It's not Na2. And so when I go to predict this, I'm going to bring it down just a little bit. It'll be Na. Alright. The D piece was Cl. Don't bring the subscript unless it's part of a polyatomic ion. The C piece was Ba. The B piece was SO4. And one thing that helps a lot of students is polyatomic ions. Go ahead and add your understood ones. So add your parentheses in the understood ones. Add this understood one here if you want. And that helps you to keep up with this is one piece. And we're bringing it over F4. It's just part of the piece. We need to figure out how many of those we have. Now I can go to my periodic table and figure out a lot of these charges using the octet rule. I can also turn around and look up my charges on my polyatomic ions. Here's a hint. The solubility tables has a lot of those charges listed. For instance, SO4 is a -2. And then if it is in the D block, the F block, or under the staircase except aluminum, in other words, something we had to use the stock naming system or the IC and the US naming systems for, that we had to do the algebra to figure it out. The nice thing about a double displacement, if I know the charge on the left hand side, I know the charge on the right hand side. That's not true for the other reactions, but a double displacement, as we have here, not too bad. So I'm going to go ahead and find these charges. So Na is in group 1, it's a +1. Cl is a -1. I'll go ahead and write those -1. Ba is in group 2, so barium is a +2, and sulfate's always a -2. Alright. I'm not a fan of that. Alright, let's look at crisscross. So bring these down. This will be 1 to 1. And this will be 2 to 2. Don't forget this ratio is 2 to 2. That's the same as 1 to 1. The ratio is not 2 to 4. There's 2 of these pieces to that. And so when I write my final answer, we will not include the charges. We can leave off those ones. And notice I left off the parentheses if it's an understood 1 out there. So if I were to rattle off the name, sodium sulfate plus barium chloride goes to sodium chloride, salt, plus barium sulfate. Notice here's our final answer. Now we want to check, make sure everything's balanced. And now in balancing, there's all kinds of ways that we can do this. I'm just going to get rid of a lot of this and rewrite it. You could follow it one element at a time, or you can start with your instructions and follow this along and do the whole setup each time. So NaCl plus BaSO4. Let's make a list. Na, I'm going to keep the polyatomic ion together because it's the same on both sides. That's one of our tricks. We had 2 main tricks to speed things up. One is polyatomic ions, keep them together. The second was this idea of least common multiples. So when I make my list for this side, remember I'm going to put a Cl down here. I'm going to put the Ba here. I'm going to try and keep things lined up. So a reminder of the math here, coefficient times subscript be the total. If it appears in more than one compound, then we'll have to add each of those. All right. Now, the first thing we want to do is figure out how many coefficients do we have. So, a reminder, there's one in front of the first compound, one after the arrow, and one after each plus. So this one has 4. So they're understood ones right now. I'm going to go ahead, let's use green here, and I'm going to add my understood ones. And just to make life a little easier, a lot of students, it just makes it click a little easier for them. Alright, so 1 times 2 gives me 2 sodiums. 1 times 1 is 1 sulfate. So that 4 can be misleading. It's part of the piece. I only have one of those pieces. 1 barium and 2 chlorines. On this side, 1 and 1, 1 barium, 1 sulfate. So now we can see, let's fix sodium first. Doesn't matter where we want to start, sodium or chlorine. I'm going to put a 2 here. That changes sodium and the chlorine. And we're done. It's that simple. Now, another thing that I often do is just follow along one thing at a time. So when I always like to start with polyatomic ions. Here's my sulfate. Make sure I have 1 on both sides. Then I did the barium. Here's barium, it's fine. Then I went to chlorine. Oh, I need 2 chlorines. Put a 2 there, that changed the sodium. Came over here, I had 2 sodiums already. So make the table out if you want, but or you can do one one at a time, whichever works best for you. You're doing the same math in your head, so it's really the same kind of problem. Alright, so balancing these, not too bad. The next reaction, N2 plus H2 goes to NH3. So what I've got is an A plus a B, and this is AB. These are combined. So this is a synthesis reaction. A plus B goes to AB. So let's go ahead and balance it. Now, we could make out our table, go through the system. It'll work, and it only takes about the same amount of time. I've got 2 free elements. It doesn't matter which one you start with. Usually I like to start with the nitrogen, and so that works out just fine. Or we can use our least common multiples. And so hydrogen comes in packs of 2 here and packs of 3 over here. And the least common multiple between 2 and 3 is 6. So I want 6 hydrogens on both sides. So I'll put a 2 here to get 6 hydrogens and a 3 here to get 6 hydrogens on this side. I now have N2 plus, oh, let's draw this a little differently. What is this saying? I've got nitrogen gas plus 3 hydrogen gases, and it's going to two ammonias. Alright, so this side has 2 nitrogens, this side has 2 nitrogens, this side has 6 total hydrogens, this side has 6 total hydrogens. A lot of times, drawing these out back to the Lewis structures from chapter 3 helps us with these. Students kind of lose track of what are the subscripts and what are these coefficients telling us. So that's what this would be if we drew it all out. So nitrogen gas plus hydrogen gas produces ammonia. Alright, not too problem. The next reaction they gave us was SO3 goes to SO2. So I've got these things combined, and I'm breaking them down to the pieces. And so this is a decomposition or an analysis reaction. AB goes to A plus B. I'm going to use the same trick. Packs of 3, packs of 2, least common multiple. I'll put a 2 here to get 6 oxygens, 3 here to get 6 oxygens. Keep in mind I now have 2 sulfurs. I'm going to come back and fix that as well. Alternatively, I could have tried to come through and do this the long way. So that was the answer we got using our trick. Let's do it the long way. See if it's really that different. Sulfur, oxygen, sulfur, oxygen. 1, 2, 3 coefficients. I've got 1 and 3 and 1 and 2 on this side. So sulfurs are done, and so I'm going to put some number here. So when I multiply it by 2, I'll get 3. In other words, 3 is equal to some number times 2. So 3/2 is what that some number is. I'm going to put my 3/2 in here, and that gives me the ratio. Now this ratio is 1 to 1 to 3/2. You cannot finish with fractions. You have to have the lowest whole number ratio. So the way to get rid of this, multiply everything by whatever's on the bottom down here. And so 2 to 2 to 3, in other words, I multiply this one by 2, this one by 2, and this one by 2, so it becomes 3. Double checking my math, I get 2 and 6, and 2 and 6. you get exactly the same answers we had before. This one had fractions. A little bit of practice, it doesn't take you any more time. So my honest advice when you're doing one of these balancing equations, you always want to include a step zero. Step zero, you look at it. You give yourself about 10, 15 seconds, no more than that. See if the answer jumps out at you. See if it's an easy one. Typically, what we see is the harder it looks, the easier it is. It's these easy looking ones that can be really difficult, okay? And take a little while. Then if you see a trick, you can use it. Our two main tricks, polyatomic ions, keep them together on both sides. The other one is this idea of least common multiple, all right? And so if you see a trick, you can use it. If you don't, you follow your steps. The steps will always get you the right answer. Always want to end up with being able to answer the questions. Are they all whole numbers? And do I have the same of each element on both sides? Okay. The next one. This should be a 2. Looks like I copied it wrong originally. K2CR04. Whew, this is a long looking one. But I've got polyatomic ions, polyatomic ions. This really comes down to AB plus CD goes to AD plus CB. Swapping partners. Alright, so A is PB, the D piece is CR04, the 4 is part of the piece. The C piece is K, don't bring that subscript. B piece is NO3. I'm bringing the 3 but not the 2 because the 2 is telling me how many I have, the 3 is part of the piece. Nice and simple. The problem here then becomes in our step 3 where we've predicted the parts, we now have to find the new subscripts. And this can be a little bit tough. Potassium is always a +1, nitrate is a -1, that's easy enough. Chromium, or chromate here, I have to look that up, but I'm going to cheat just a little bit, and I'm going to go down to my solubility rules. And I happen to see on my solubility rules, one of these rules for an insoluble compound, it says CrO4, and it has a -2. So even though this wasn't one of the polyatomic ions that we had to memorize, it's listed back there to show me that it's got -2. If I wasn't sure, I can go to table 3.3 in our book. It was one of those that wasn't in red. Alright? The problem is we need this charge so that we can do our crisscross. And I can't find that charge here because I don't know the subscripts. The math on this is normally subscript times charge plus subscript times charge equals the total charge. We don't have those subscripts, but we do have it up here on the reactant side. And so if I can figure out this charge, it'll be the same because this is a double displacement. So I've got 1 lead here plus 2 nitrates. Each nitrate is a -1. That's where that -1 came from. Alright, and the total charge, I don't see one. It would be there if I had it, and so this is equal to 0. If there was a charge, I'd set it equal to whatever that charge is. X minus 2 equals 0, so X comes out to be 2. Why is that important? Down here, X is 2. When I crisscross, I'll get 2 to 2, which is the same as 1 to 1. So PbCrO4 plus KNO3, 1 to 1 on this side, we're good. So then it asks us to name them. Don't forget, when you name things, you're going to have to have the stock system for lead because it's in the D block or under the staircase except aluminum, or the F block, right? D block, F block, under the staircase except aluminum. So I'm worried about my lead. I've got to figure out the charge. We already did that math. It's the same math. This is what we did for finding that charge for the naming. So this would be lead 2 nitrate plus potassium chromate. Notice potassium, I didn't have to give the charge. It's not potassium 1 chromate. Potassium's always a plus 1. So just potassium chromate. So when I do this one, lead 2 chromate, even though there's only one lead, it's the 2. The charge is what goes in the parentheses. It's chromate, like that. There we go. And potassium nitrate. All right. So that one, a little more involved. Still good practice though. All right. So let's see, what else did we have? One that they love to ask. Oh, this shows up in so many pre-labs. Let's look at it because students miss this day in and day out. Step back and let it focus. It refuses to focus. Focus. Alright. It's probably what we know. So aluminum to HCl. Oof. A plus BC. There it goes. Alright. So A plus BC, this is a single displacement. Alright. So this pieces should be AC plus B. So I'll have my aluminum, the C piece is Cl plus the B piece is H. Most students get this part fine. It's the next part that students really struggle with. And this is the part why we ask this one so often. Aluminum is a 0 over here. On this side, it's going to have some kind of positive charge. Aluminum happens to always be plus 3. Alright. They also like to use group 2 in this reaction. Really common single displacement type of reaction. Over here, my hydrogen actually has a plus 1 kind of charge, and chlorine has a minus 1. Over here, hydrogen is 0. And hydrogen, when it's by itself, anytime it's by itself, it's diatomic. And that's the part that students always miss. Hydrogen is diatomic. Chlorine is a minus 1 on both sides. It's just along for the ride. So it's this 3 and this 2. When I crisscross, that's the part people miss. Don't forget, when you bring this down, it's not a negative 1. You can't have a negative number of atoms. You've either got it or you don't. Alright, I've got these two together on this side, 1 to 1, packs of 3, packs of 2. Immediately I say, hey, I'm going to use my least common multiples. And so 6 hydrogens, 6 chlorines on both sides. So 6 chlorines, now 3 here to get 6 hydrogens. Now I've got 2 aluminums. I need to come to the other side and put a 2 here. Had I not done that trick, this would have been a 2 and a 3 and a 1, and this would have been 1, 1, 1. And so I would have, I'll do it in green. I would have come in and had to hydrogen and chlorine. The chlorine I would have probably done first, and I would have put a 3 over here to give me 3 on this side and 3 on this side. And I wanted to do hydrogen last because it's a free element, and I could do 3 halves on this side, and that would give me 3 over here as well. So my ratio would have been 1 to 3 to 1 to 3 halves. Can't end with that ratio, so I'm going to multiply all the coefficients by 2. In other words, 2 to 6 to 2 to 3, which is what we got. So a lot of students are intimidated by the fractions. They're not that difficult. It's the same algebra. All we did was 3 equal to x times 2. This is where the 2 came from. This was our x. Okay. So that reaction you will see again. If not this test, you will see it on the final. If not, I'll tell you, we swap it every couple of years. It's either on the final, and in the years that it's on the final, I like to put it a slightly different one like it on the test. If it's on the test, we'll usually swap and put a different one in the final. It'll come up again in the pre-lab, something like 2 labs in a row here. So we'll see it again. All right, so not a problem. Last one we had, there was, it asked us burning C10 H22 plus O2 goes to CO2 plus H2O. Combustion. 1, 2, 3, 4 coefficients. All right. Combustion reactions, I like to go ahead and make my table. 1, 2, and a lot of students ask the question, how do I get 3 here? Don't forget, there's 2 hydrogens there, and 2 oxygens there, and 1 oxygen over here. So 1 times 2 plus 1 times 1. 1 times 2 plus 1 times 1. That's where this 3 came from. Because it's in both places, we have to do the math for both sides. Okay? For both compounds. On this side, 10, 22, and 2. 1 times 10, 1 times 22, 1 times 2. Easy. Alright. I'm going to start with the carbon. I'm saving oxygen for last. It's a free element. I would like to do it last. So I'm going to I need 10 carbons. Put a 10 over here. That makes this 10. It also changes my oxygens. Normally, if I'm doing these, I wait and I do that after I've done the hydrogens, but we can go ahead and do that. That changed this one to a 10. So it's 10 times 2 plus 1 times 1. That'll be 21. Alright. To fix the hydrogens, some number times 2 to get 22. That's an 11. Alright, so that'll give me 22 here. So my math now is 10 times 2 plus 11 times 1. Notice I'm doing the math again. I'm not trying to adjust my previous answer. I'm not going to try to change the 21. I'm going to go ahead and do the math again. So 20 plus 11 is 31. Okay, so we didn't add 11 more. We only added 10 more. We already had one. Alright, so I now need some number. So then when I put it here, some number, when I multiply it by that 2, I want it to come out to be 31. Easy enough. X will be 31 halves. Don't put that in your calculator. Don't write down that it's 15.5. Put 31 over 2. Because the next thing I'm going to do is multiply them all to get them. I've got 1 to 31 halves to 10 to 11. I want them all to be whole numbers. I'm going to come through, multiply them. Oop. My pens are running away on me. Multiply them all by 2. So this will be a 2 times 1. This becomes 31. I just canceled out the 2 on the bottom. 20, 22. Better double check. That's a lot of math going on. So 2 times 10 is 20. 2 times 22 is 44. 31 times 2. Oh, I got my socks off. I can count. Okay, so it's 62. 20 times 1 is 20. And 22 times 2 is 44. And then, this math. Let's go ahead and jot it down out here. 20 times 2 plus 22 times 1. 40 plus 22 is 62. Ask myself the question. Are these all whole numbers? Is it the lowest common multiple? Well, this one isn't odd. The rest of them I can divide by 2, but that's it. So, yeah, lowest whole number ratio. I have the same elements on both sides. Tells me I balanced it correctly. Oh, powerful feeling. Powerful feeling. There's a reason why once you get it to click and once you've practiced, you'll want a lot of bouncing chemical reactions. We usually don't put a whole ton of them on the test because they sometimes take time. What you do not want to do is to get on the test and freak out and say, I just don't see the answer. Alright? So, when you're doing these, always leave yourself time and just start the process. Alright? So, if you look at them, there's the series of steps will get you through it. But, there's tricks. Don't look all day at it. If you don't see the trick, just start the problem. It's not that much worse. All right. The pre-lab also goes into what are the signs of a reaction, and this is a great thing to get ready for our class. So, signs of a reaction. It talks about one is a color change. If I were to take my coffee and add a bunch of water, it would get lighter. All right. That is not a color change, that's a dilution. So if I take grape Kool-Aid and it's dark purple and I add in some water, it's just going to get lighter purple, not a color change. Now if I add in a liquid and it was blue and then now all of a sudden it has no color, all the color went away, then assuming it wasn't a large dilution, it's a color change. If it had no color and it becomes blue or red or green, that's a color change. If it was red and it turns blue, that's a color change. So we're not looking for any kind of just dilution. So this is Beer's law is what it really comes down to. A equals ABC, my favorite law. So Beer's law just tells me that if I dilute something out, I'm going to lower its concentration, it's not going to absorb as much light. You're not going to see as much color. All right. So color change, obvious color change, has to actually be a different color. We're looking for absence of color to having a color, or red to blue, or something like that. All right. Gas. If you see bubbles, it's a sign of a reaction. You have to be a little bit careful. If you just pour things in, a lot of times just the mixing process generates a few bubbles. But we're going to be looking for a lot of bubbles. And some of these reactions take a while to kind of get fired up and get started. And so we're going to be watching it for a little while. The bubbling sometimes takes a little bit of time to get started. Okay, so you see bubbles, that's a sign of a reaction. A temperature change. Yes, it's a great sign of a reaction. We'll actually use that later. But in the experiments when we're doing small scale in a test tube, believe it or not, if I take this pen and I say, okay, it feels kind of cool, and I hold it in my hand and I wait on the reaction to take place, and then I feel this and go, hey, it feels a little warmer, and I let somebody else feel it and they go, oh yeah, it's much warmer than it was. It's not necessarily that the reaction got hot, it's I warmed it up with my hand. So unless we get a large change in temperature, it's a little bit difficult to tell, especially on small scale. So we're going to be, we'll have one of these reactions does a temperature change. You can't really tell it. Precipitation reactions. If it forms a precipitate, remember a solid is a precipitate. If it forms that, it's a sign of a reaction. Can't always predict. Maybe it forms two solids. So you're going to have to be careful about precipitation reactions. A lot of times you'll just take the test tube, shake it around, and then if it's stuck up on the sides, that'll be how you can tell it's a solid. Sometimes things form gels where the solid is kind of dispersed, and just like Jello, they spelled it wrong so they could trademark it. But one of these reactions that we're looking at actually does that. So it's some neat stuff. I'll post a video on those kind of reactions. All right. So that gets us kind of caught up in terms of where we're at on net ionic equations and putting these together. And so we're ready to get into putting these together with the math and practicing. And what we're really going to be doing is taking this mole-to-mole relationship, and we were getting it from the chemical formula. We'll now be able to use the coefficients from the balanced chemical equation, and we can use the reactants to the products, or be going from one reactant to another reactant. And so these problems aren't any more difficult than what we saw in the first part of this chapter, but only thing new is you sometimes have to balance the chemical equation and kind of combine these ideas. And so we'll make another video for that, and getting into that, into our theoretical and actual yield, and the really scary looking stuff, and that scary stuff we'll do next chapter, or not next chapter, next video. It's called stoichiometry, and it sounds difficult, but if you've ever planned a cookout or a meal, or you're trying to decide, hey, how many rolls of toilet paper do I need to buy, you've done this kind of math. It's not that difficult. Alright, so I'll get this one posted, and I'll get you a new one recorded here shortly.